Okay, hi. So we were ended up with some R commands for how to compute the correlation transformation for vectors, and we used Y as an example, but they could have been predictor vectors too, predictor variables. And now we said we wanted to turn our attention to the linear model with the standardized variables again. That was a little detour of definitions, basically. Well, the standardized regression model just uses all the starred variables that we just talked about from the correlation transformation. In other words, yi star equals beta 1 star plus xi 1 star plus dot 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 plus beta p minus 1 star xi p minus 1 star plus a new error term epsilon I star. And we'll call this the standardized MLR model. One obvious thing that hits you is there's no beta 0 star, and the reason is, this is just a little algebra to see it, that beta 0 star, while you could include it, little b 0 star, the estimated beta 0 star, will always be 0 due to the standardization. By doing this, by standardizing this, aligning everything and centering it, it forces the least squares plane, hyperplane, to go through the origin. So we can just take beta 0 star out right from the beginning, and it does make the model slightly simpler. All right, so with that, how are these regression coefficients related to our old beta 0, beta 1, etc. So the first question is, so we just have to hack it out. So to find a relationship between beta 0, beta 1, beta p minus 1, beta 1 star, beta p minus 1 star, we just have to do a little work. So we have, using the model above, yi star, right? Yi star is equal to this. So let me just substitute in the definition. So yi star, so this is just yi minus y bar over the square root sum yi minus y bar squared. And we'll know these are 1 to n. We don't need to clutter everything and write that every time. Okay, so we have that is equal to, now over here I have beta 1 star xi1 star plus. So let's write this on this side with the summation notation to make it a little less cluttered. So this is equal to, I'll write summation k equals 1 to p minus 1. And here I have my beta k star. And for my x, I have that thing that looks very similar over here. I have xik. Let's see. I have xik minus xk bar, because I'm just talking about the I term. There'll be an equation for each I, for 1 to n. And now I divide by the sum xik. I could use j, but it doesn't matter. It's just a different I in here. Well, maybe I should use j. Xk bar squared. Okay, let's see. Does that look right? Yeah, that looks right. And now I have plus my error term over here. Okay. That looks right. Looks okay, right? Now, on this side, what I want to do now is I want to isolate the yi. The idea is I'm trying to make this look like the original equation So I want to isolate yi on the left. So isolating yi, I get, let's try to write on the page where you can see yi equals, I multiply by this, and I add y bar. So I have a y bar first, and now I have plus. I still have this big sum over here. K equals 1 to p minus 1 beta k star. And I've multiplied by this. So I'm going to write this like this. I have sum yj minus y bar squared over, what the hell? I'm running out of ink. Okay, hold on. Let me just go get it. Go get another pen. If there are any. What the? Oh my God. Hold on. Okay. Okay, so I think I got one that writes, otherwise we'll be done. But with the quarantine, I don't know. Y squared, so I'm just multiplying through by this on this side. So I have this over the sum xjk minus xk squared. And here I have this xik minus xk bar. This is outside the square root plus epsilon I star, right? So I have these terms. So look, I have the yi here, and I have the xik's here. So we do want to separate these. Here I have the xk bar. So I will separate those into two terms. I have yi equals y bar minus summation k equal 1 to p minus 1. And we're taking the bar here. So I have beta k star, this big sum, and now I have my xk bar, and I have plus sum k equals 1, p minus 1, beta k star, sum yj minus y bar squared over sum xjk minus xk squared, xk bar squared, and plus the error term. Okay, look. Wait, where did I write my xik? Okay, here's my xik in here, right? Xik, I need that in there too. That's the whole reason I did this, right? This xik is here, and now I can see the coefficient of xik. So that was the reason for all that ugliness. I now have a relationship. So here's why this should look a lot like the regular model now. This was what all that work was for. I have a constant piece here. This is a constant. And over here I have a linear term, a linear combination of the xiks, right? These are the coefficients of the xiks. So these are what are these? Looks like a heart, right? What are these? These are the beta k's, right? So from looking at this, so we see beta k is equal to bk star times the ugly square root yj minus y bar squared over sum xjk minus xk bar squared. Okay, or equivalently, I could divide each of these by the square root of n, and just have a little shorthand way of writing it. Or we could write bk is equal to beta k star, and I could just write this as sy over sk. Each would have a square root of n minus 1 in the denominator, but they would cancel, so I could write this sy over sk. Okay, and this is for k equal 1, p minus 1. All right, so now if I group the other terms, the first two terms here, I find my b0, right? So grouping the first two terms. Also, beta 0, which should be the constant, is this. And this is not necessarily 0, but it is y bar minus the sum, k equals 1, p minus 1. And you can, again, see, if you want, for simplicity, that each of these is sy over sk. So actually, each one of these terms here, each one of the beta k stars sy over sk is just beta k. So this is y bar beta k, which I've already computed, and xk bar. Now, you might remember, that since little b0 is always the fitted regression plane always lands on the means, so this is b0 is always equal to this, k equals 1 to n minus 1, bk xk bar. So since this is always true by least squares property, this implies that there is no other term needed in the, so this implies there's no other term needed in the standardized model. So this implies no other term, b0 star, required, needed in standardized MLR model. We already have the right little b0 here. We can see this. No, it's not. If you're unsatisfied with this explanation, you're free to pursue it more and try to convince yourself of it. Okay, stop now and do one or two more on this.